Hi, y'all. So we're going to be starting on chapter 3, which is motion in two or three dimensions. And really, the primary thing we're going to talk about in this chapter is projectile motion, which is motion of something that's only under the influence of gravity near Earth's surface. So that's really going to be our focus. All right, let's see if I can. There we go. All right, so these equations should look really familiar. These are just our kinematic equations, and you notice specifically that these are for the x directions. I've got x subscripts everywhere. Let's see, my displacement is delta x, and so on and so forth. And of course, I can have the exact same equations, in the y directions, and there you go. I just switched it, and if you blinked, you missed it, right? But there we are. So equations of kinematic equations in both x and y directions. All right, so let's take a look at this. If we've got motion in two directions, we can really treat the motion in the individual directions, in the x direction and the y direction, independently. We really can just split the x parts and y parts up and kind of analyze the x part and then analyze the y part separately and then recombine them if needed. But we really can treat them independently. And we'll see what that means as we go through and we do some example problems. All right, well, how are we going to approach these kind of problems where we've got motion in two dimensions? It's the exact same steps, more or less, that we used last chapter. We're going to make a drawing. We're going to make a table of values, for our 5 kinematic variables. But we're going to make 2 different tables. We're going to make a table for the x direction and a table for the y direction as well. So rather than just the one table that we saw last chapter, we'll make tables for x and y. Really, it's the exact same problem-solving steps. All right. So if we're dealing with projectile motion, what's that mean again? That means that we're just worried about the only thing that's influencing our object that we're analyzing is gravity. And specifically, gravity near the surface of Earth. What do I mean by near the surface of the Earth? Really, honestly, this acceleration of 9.8 meters per second squared, at least the size of it is 9.8 meters per second squared, is pretty close to true for like a mile up above the Earth's surface. So, I mean, there's a little bit of variation there, but at least if we're anywhere near the Earth's surface at all, this value of 9.8 meters per second squared for the magnitude of the acceleration in the y direction is absolutely valid. So that's great. That's going to be our acceleration in the y direction is negative 9.8 meters per second squared. What about the acceleration in the x direction? Well, if I picture throwing a ball or something else, and once the ball leaves my hand, the only thing that's influencing the ball is gravity. Neglecting air resistance, which is really pretty small in most cases, unless we get going really high speeds. Well, if that's the case, there's no acceleration in the x direction at all once the ball is in the air, or once the dart leaves the gun, or whatever. Once the diver jumps off the board, there's no acceleration in the x direction. All the acceleration is in the y direction. That's exactly what we see here in this picture. You notice that all the acceleration arrows are pointed downwards towards the surface of the Earth. That's always going to be true when we're in projectile motion, and that's something that you guys will get to do a little video analysis on in the next lab. Right. Okay, so again, here's projectile motion. When gravity is the only thing influencing our object, acceleration is downwards in the y direction with a size of 9.8 meters per second squared. There is no acceleration in the x direction at all. That's 0. And as a result, if there's no acceleration in the x direction, our velocity in the x direction is constant. All right. Let's see what effect that has on our kinematic equations. All right. So there's our velocity in the, there's our kinematic equations, easy for me to say, in the y direction. Well, what about the x direction? Well, let's see. If I start trying to think about writing these things out and keeping in mind that, okay, my acceleration is, if I'm worried about acceleration in the x direction is always going to be 0. Let's look at what happens with that first one. I end up getting, well, Vx is equal to V naught x. Why? Because the acceleration is 0 and plus at would give me 0. All right. Well, what about the second one? Well, this would give me delta x is equal to 1/2 V naught x plus Vx times delta t. Well, let's see, the velocity in the x direction isn't changing at all. So V naught x and Vx are going to be the exact same thing. So let's see, if I think about what happens then, if they're the exact same thing, I might as well just say 2Vx there. Then I've got 2 times the 1/2. That gives me delta x is equal to, well, Vx delta t. Or I could have said delta x is equal to V naught x delta t. Whatever, doesn't matter. What about the next equation? Okay, this one, I've got that acceleration in there again. Of course, yeah, I know I'm using the y equations to talk about the motion in the x direction. Hopefully y'all can see what I'm doing here. But if I stick in, if I'm worried about the x direction and my acceleration 0, that third equation is just going to reduce to Vx squared is equal to V naught x squared. Oh, my velocity stays the same. Look at that. These guys are basically the same thing. Take the root, they're the same thing. All right, well, what about the last one? Again, let's see, my acceleration in the x direction would be 0. And this guy right here would just reduce to delta x is equal to V naught x delta t. And if you look at that one, let's put a box around this guy right there and a box around this guy right there. They're the exact same expression, keeping in mind that the velocity in the x direction doesn't change. So I did all of that just so that I could do that right there. All right. So when we're dealing with projectile motion, all of those equations in the x direction collapse to become just this single one right there. All right. So these are equations that we're going to use for projectile motion in the y direction and in the x direction. And those are the tools that we will have. All right, this does it for this one. I will be showing a little demo video in class tomorrow, and we will analyze some motion. So I'm going to try and stop this right here.